These notes are already online. The video will be. I am. It's okay. We love stupid questions. Okay. Physical equilibria. This is probably like the only thing you're going to see about physical equilibria because we're not going to get to this until March about how solids, liquids, and gases change phase and a little bit more information about that. But physical equilibria is just changing state. So obviously in this example, what phase changes are going on? Phase changes. So what's the phase change called? Vaporization and condensation. Okay, so equilibrium, just all the definition of equilibrium means is the rate of the forward reaction equals the rate of the reverse reaction. So the rate of vaporization or evaporation equals the rate of condensation. Okay, so this is physical equilibrium between the water liquid and water gaseous state. That's pretty easy because we know that like if you have a closed water bottle and it goes out in the sun, you'll start to see you can't really see it vaporize, but you can see the result of vaporization, which is the condensation on the outside of your or on the inside of your water bottle. So what's happening is it's vaporizing, so it's coming out of solution, and then in the vapor state, it's just you can't see it. But what then really automatically happens is it condenses on the side of the flask or the side of your water bottle, and it's going to appear as a bubble, as a drop of water. So this one's pretty easy to see. But everything here for equilibrium to take place, it has to be a closed container. Because what happens if it's an open container? What happens to the vapors? They escape. They never actually have the chance to reverse the reaction or reverse and turn back into the liquid state. Okay. This is a random question about vapor pressure. High vapor pressure or low vapor pressure? What does water have? Make a choice. Water has a high vapor pressure or a low vapor pressure? Who says high? Who says low? Majority rules. Okay, why low? If you open a bottle of water, you smell it? No, you can't smell it. It's not vaporizing. If you open a bottle of like fingernail polish remover or acetone, do you smell it? Yeah, it like hits you in the face, right? Okay, that's because it's vaporizing readily. Like it's really, really fast vaporizing. So if it's vaporizing really fast, if it were in a closed container, would it create a lot of pressure? Yes, because the gases are beating on the sides of the container. So high vapor pressure, VP equals very volatile. Low vapor pressure means not volatile. So water doesn't really vaporize that quickly. That's why you can water your plants like, once a week, once every 2 weeks. That's why if you have like, if I had a glass of water sitting out here, it would be here next week after. It's not going to vaporize that quickly. If I put a little container of like, some sort of alcohol, like isopropyl alcohol, anything like that, it's going to vaporize probably within 2 days. So it'll just be up in the air. Okay, so more on this. We're going to talk about KSP and how solubility is just a relative term. It's comparing to how many particles actually do dissolve from the solid versus how many do not. So sodium chloride is very soluble. So we can have sodium chloride in water. It can make the two ions. It can also reverse though. So these particles, if we took some of the water out, if we let it dehydrate, there's not as much space for the ions to exist, so they revert back to their original form, which is the solid state. You can see that like whenever you go get seashells at the beach, you pick up the seashells, they're nice and pretty, they got a little like salt water on it, put it in a bag, you take it home, and take the shell out again. It's probably got some like crunchy salt on it, because there's no longer an aqueous solution on the seashell. It's now dehydrated to the point where it's back to salt itself. So you see that a lot. This is all I'm going to say on physical though. We're going to get really deep into the chemical equilibrium. Cool? Okay. And this is the first thing. Did everybody pick up sheets when you walked in? I see. Anybody else use one of these?
Wait, are we actually dancing?
No, we're not dancing. We'll dance tomorrow probably. We're going to YouTube. I mean,
You just
I might teach you how to dance. It's an exercise in It's an exercise in chemistry and social awkwardness.
You're not recorded though.
Okay, so chemical equilibrium. The opposite of chemical equilibrium is when something goes to completion. So in a problem, if it actually says, this reaction goes to completion, it is not an equilibrium problem. If you see it goes to completion, it's not equilibrium. Okay, when it says it goes to completion, it means it makes all products and 0% reactants are left. Okay, so there's nothing to go back and forth with because you have all products and no reactants. This is a prime example of that. Because water like at room temperature does not revert back to hydrogen gas and oxygen gas. Because if it did, things would be catching on fire all over the place. You rub your hands together, your hands would poof on fire. Because your hands have a little water on them, they would revert back with the friction. So this does not happen. It does not have a reversible arrow on it. It's just two completions and that's it. Opposite of that would be things reaching equilibrium, where it's able to revert back and forth between the forward and reverse reaction. We draw it as a reversible arrow like that, like this, or I like to do it like that. Half arrows. I'm lazy. Okay, so those are the three ways you'll see the reversible reactions. So in this case, nitrogen dioxide, whatever that is, tetroxide, do revert back and forth. So I'm going to show you how I kind of set this up in a ice box. I'm doing this on the board, so we will share this with our viewers online later. Okay, so here's my reaction. This one actually is telling me some information. So it's saying I begin with 0.07 moles of NO2. So I'm going to write that kind of like a before, during, and after, but I'm going to call it ice. Cool? Ice. Okay. So here's 0.0700 moles. If it tells me that I don't have, it doesn't tell me anything else, then I'm going to assume I have nothing of the product present. I'm just showing you how I can start with a reactant and get to equilibrium. And then the next example, I'll show you how I start with a product and still can get to the same exact equilibrium. Okay, so I'm starting with 0 of that. It tells me, though, I'm going to form 0.0116 moles of that and 0.0292 moles of that. So I'm going to form that at equilibrium at the end. This is essentially saying before, during, and after, except we're just calling after equilibrium now. So here, what am I forming? 0.0116 moles. And here I'm forming 0.0292 moles. Somebody tell me, how did I get from here to here? What did I add over here? I added 0.0292 moles. What did I subtract total right here? I mean, you can do your calculator. Right?
408.
How much?
0.0408.
No.
It's a 5. I have this for you. 0.058. 84. Okay. So minus the total. The tired one back there gets it. Okay. Oh, hold on. That's X. I'll tell you what X is. Okay. So this right here, since you see you have a ratio of 2 to 1 here, you're going to call what you're adding over here, since there's a 1 there, you're going to call it like adding 1x. Okay? You're adding a certain portion here, but you're minusing a double that portion over here. Okay? So from here to here, I think it was right. It was 0.0584, I think is what Nathan said. So that's what 2x is equal to. Well, guess what x is equal to? What's x equal to? 0.0292, which should be this times 2 will equal this. That's how we got there. Okay, so you can actually figure out the amount of change when you have one condition given to you or the other, and you can go back and forth because you'll figure out what x is based on the ratios of the reactants and products. For the second example, I'll do that one over here. We're going to begin with a different scenario. You're beginning with you're beginning with only product and no reactants. It doesn't tell you you're starting with anything. So we're calling that initial change in equilibrium again. What are we ending with? So same scenario, right? And 0.0116 moles here. All right, so in this case, we're not going in the forward direction. We're going in the reverse direction. We're starting with the products, and we're going to form reactants. So this is reacting. Are we subtracting from the side or adding to the side? Subtracting. We're subtracting a certain amount called x, 1x to be specific. That amount is equal to whatever that difference is. That difference is 0.0058 moles. And on this side, we're adding to this side, because we start with 0, we have to add. You're adding double that, because you're adding the amount of 2x over here. 2x is equal to that times 2, which is 0.0116 moles, because that's what this final answer is representing as well. So it's just like before, during, and after. We call it something different, and it's representing a very special condition called equilibrium.
So will it always be like you're given the
No. You will be given concentrations sometimes, and sometimes you'll be given something called the K constant, the equilibrium constant, and you can revert backwards. I'm going to show you how to get there, okay? Question?
Is this the part?
Yes. It's called icebox. All right, questions here. I essentially showed you how to do an icebox. I'll show you a couple more, but you'll know how to do this after today. Do not write all of this down. Write down what you need. Homo means what? Same. Okay, that means in a system, an equilibrium system, everything's the same state. So homogeneous equilibrium systems have the same state. Usually it's gaseous because it's hard to have all liquids or all solids. The solids don't really react without something. Gases have such high kinetic energy that they actually react upon collision. Hetero means different, so you've got different states present. Usually it's going to be a gas, well, sometimes it's gas and liquid. A lot of times you'll see solid and liquid. A good example of solid and liquid would be a KSP situation, a solubility constant, where you have an insoluble product. Like, what's a good example of something insoluble? Calcium hydroxide is very insoluble. Yes, it's still a strong base. We're going to do a KSP lab with that after Thanksgiving. Okay, so calcium hydroxide is very insoluble, but it just a little bitty bit of it does dissolve. So when it dissolves, it makes ions. So that would be a solid and aqueous, or liquid heterogeneous equilibrium. Another example is this one right here, calcium carbonate making solid and gas. So that gas right there is just representing the other state there. So remember me telling you about in kinetics where you could use pressures in your rate law constants or in your rate laws for gases? Anybody else remember that? Okay, that's because it's really hard to find the concentration of a gas. Like you need moles and you need liters. It's not always that way for gases. So a lot of the times you'll use partial pressure for gases, and I just want to remind you how to write partial pressure. Like partial pressure is big P with like a little subscript of what the gas is that you're indicating. Don't forget that. You'll write that a lot today. Aqueous solutions, you'll use molar concentration, so you'll be representing it with boxes. Box brackets. This are just the different types of equilibria we're going to get to. We'll get to acid-base equilibria and buffers next unit. So like we'll do like 2 weeks on general equilibrium and then 2 weeks on complicated equilibrium. Acid-base equilibrium. Can I go forward? Almost. Okay. All right, go back. Somebody tell me what the definition of equilibrium was. It may have been, well, actually, keep reading, guys. Maybe you remember it. Yeah.
Forward reaction equals rate of reversion.
Yes. Yes. I think I have it on my slide. Yes. Right there. Okay. So when the rate of forward reaction equals the rate of reverse reaction. Rate. What does that sound like? What unit? No, I'm sorry. What? Kinetic. Something in unit, not chemistry unit, but like unit that we just completed in chemistry subject area. Thank you. All right. So with the rate of forward, I'm going to take up all this space. So forget this graph for a second. The rate of the forward equals the rate of the reverse reaction. That's what equilibrium is. So it's dealing with rates, which is dealing with kinetics. But what is? Let me give you an example. Let me give you a reaction of gaseous A reacts to make gaseous T. It's the easiest reaction I can give you. Don't worry about what it is. If these are our reactants and products here produced, let's substitute in here the rate law. Assuming this is a slow step or something, it's got a 1 here and a 1 here. So how did our rate laws usually look? Rate equals what? K forward times what? The reactant. The reactant for the forward reaction is A to the first, right? All right. This one? K reverse equal our times. Yeah. Okay, so B in that case for the reverse reaction, B is the reactant, even though it's on the product side. Comfortable with that? Sometimes that's like, no, it's the product because it's on the right side. When it's going the reverse direction, this is the reactant. Okay, so now I've set K forward equals, rate of forward equals rate of reverse, and I've put in the rate laws. I want you to isolate, put the concentrations on one side and the K's on the other. What do you want to do? Divide by? Okay, I'm going to divide the K just I want to show you one specific way, and then I'll show you the other way. I'm going to divide by K on this side first, and then divide by A on this side. So what cancels over here? A. What cancels over here? KR. So that leaves us K forward over K reverse equals the concentration of B over concentration of A. All right, the significance of this is to show you that when the rates are equal, these two K's will be equal because the rates of this, or the rate constants of this particular reaction should be equal. They might be reverse in sign or something like that. But this, we're going to reduce and call it big K equilibrium. So the K's that we use in rates were lowercase k's. The K's that we use in equilibrium are big K's. They're just not enough letters to go around for chemists. They choose the same letter, they just make them different sizes. Okay, so K equilibrium is a big case K. The equilibrium constant is what we're going to use extensively the rest of the day. It's equal to the concentration of the products divided by the concentration of the reactants. Do you see how this matches my BCE? The concentration of B over the concentration of A, which is the concentration of the products over the concentration of the reactants. So I can take rate stuff and I can change and manipulate the variables and call it equilibrium now because they're all definitely intertwined and interrelated. So what we're going to start using is the big K, and we're going to start using the products of reactants. I'm going to do a lot more with this on like the next 2 slides. I just want to go ahead and show you this now to show you how the definitions are, how they're intertwined. One more thing with this is whenever we drew these kind of in kinetics, when I have reactants present and no products, what is my graph of concentration versus time start as? What happens to reactants over time? They decrease. So maybe they start up here and they go down in time. Then they start to maybe level off. Okay, so these are reactants. As the reactants react, what are they forming? Products. So they start at nothing, and they're going to increase and increase and increase. And once the reactants stop changing, the products also have to stop changing. Why? There may be some to make them, but the reactants are not changing concentration, therefore they can't be making products if the reactants aren't changing. Like it's a 2H street. So the point at which the rates stop changing, about right, I'd say like right there on the flat lines there, that is called equilibrium. Where the rate of the forward equals the rate of the reverse, the concentrations now, because remember this axis over here, this axis is concentration. When the concentrations are constant, the rates stop changing, that is called equilibrium. Yes. You don't know what my time is, so this could be a nanosecond. I don't know. It doesn't. This equilibrium doesn't relate to how fast it goes at all. The K's in the rate laws do. So a lot of times when we try to make assumptions about how they are connected, we can say they're connected, but don't make assumptions about too much stuff. All right, so know how those graphs look because we're going to college tomorrow. All right, and then the concentrations are constant. So like you can see these concentrations are flatline now; they are constant. But like what can happen is one reactant can form one product, and then immediately one product will go back and form one reactant. So I can give Molly $1. She's got $1 for like a nanosecond, and then she gives me the $1 back. Is there a net change? No. So it's called no net change. But the reason the whole word dynamic is in there is important. What does dynamic mean? It's constantly changing. It's frantic. It's very interactive. It's very sporadic. Dynamic means it's constantly changing. So the concentrations are constantly changing, but it's like a net change of 0. Cool? Okay. Graph. Okay, so here you can see is this a reactant or product here? Reactant's going down, right? That's H2. Well, tell me what you notice about the difference between H2 and N2. Okay, you have more to start with, but it decreases at faster rate. How fast? How much faster? Twice as fast? 3 times as fast. This is 3 times as fast decrease than the N2 is decreasing. Okay? Why? Because it's a 3-to-1 ratio. All right. Tell me about the relationship between N2's graph and H3's graph. All right, this is forming twice as fast as compared to this decreasing. Okay, that's because it's a 1 to 2 ratio. All right, so remember how to read your graphs, and then notice that at equilibrium, it's when all three of them flatline, they stop changing concentrations. Another version of this, I'm just going to show you this one now. This reaction is just H2 plus I2 yields hydrochloric acid. This is the reverse of that. I don't like that they wrote it that way. I'm still going to write it this way because I don't want you to think that you can just change the way you write it. It's still written this way. It's just that they're reversible. Okay, so at this point, you're starting off with your reactants. They're going down. You're forming your products. At this point, you've started with two different situations, two different concentrations than this graph. But what do you notice about the two graphs? Same equilibrium position or equilibrium state. So even though I'm starting off with really crazy concentrations here and very drastically different ones here, they come to the point of equilibrium at the same exact state, which makes this system have the same K of the products concentration over the over the concentration of the reactants. So in this case, the red line is the product and the green line are the reactants. This is concentration over here, right? So this number is this number here in this reactant. Is this the reactant concentration here? Since it's the same here and here, there is one K value, equilibrium constant, for any given BC, for any given situation, any given system. Okay, so they might look very different, but they'll end up the same. In this case, HI is what you're starting with, so it's acting at it's the product in the reaction in the BCE, but it's acting as a reactant because that's the only thing you're starting with. Anything we start with, we call it a reactant.
Okay, but like on the in equation.
This is still written the same way, yeah. Products over reactants.
So, but like the products in that equation are the products in
the BCE. It's still HI over H2 and I2. Yeah.
Why did that graph so
because it's still talking about that compound of HI. It's just, I'm telling us that we're starting at a much higher concentration. I've totally changed the initial concentrations of everything here, but what happens is they come to equilibrium in the same manner. They both stop at the concentrations at which the equilibrium decides.
looking at the reverse graph based on how much concentration
Yeah, you start with, yeah. Yeah. This one probably proceeded faster, and you can see that because the slope is drastically different. Yeah.
So even though HI is acting as a reactant in the second graph, it's still going on with the product.
Because it's the product in the BCE for that system. It is. That's why I said I don't like the way they wrote that because it's misleading. So I rephrase it. All right, good questions, guys. This is just some like multiple choice conceptual stuff that you probably want to know. And I've told you a lot of this, so if you want to write it down again, you can. But first of all, equilibrium means there are products and reactants present, both of them. Okay. If it went to completion, it means all the reactants are gone, and that's not the case here. Second, there's no net change. That was my dollar situation with Molly. I gave her $1, she gave me $1 back. I gave her $1, she gave me $1 back. There's no net change. It can still change though because it's dynamic. Dynamic means it's constantly changing. It's just no net, no overall change. Net also means overall. Since it's a closed system, products and reactants are not escaping the reaction vessel. So it's a closed system. That means the number of particles will stay the same no matter what. They're just kind of changing their location or changing the way that they look. One of the big, I put this in red, okay, this is bad. A lot of people think, oh, it's at equilibrium, everything's equal, they're nice and happy. That's a big misconception, okay? So when you're at equilibrium, the products do not equal, the concentration of the products do not equal the concentration of the reactants. We just saw in those graphs, they were very different. It's just the rates at which they are forming is the same. A lot of people think that. It's like, oh, equilibrium means everything's equal, it's a happy place. Okay, so don't think that. And then the way this equilibrium position is written, a lot of times you'll see just the arrow like that. You'll see my little funky arrows like this. But what if I write an arrow? It's got a big arrow pointing this way and a little arrow pointing that way. Which side is favored?
The big one.
The products, the forward reaction, right? So the products are favored. And if I wrote it, it's hard, like that.
The reverse is big.
Reactants are favored, or the reverse reaction is favored.
What do you mean by
Favored means I'm producing more products than I will have reactants left. Reactants favored mean I'll leave more reactants and have products produced. I'm gonna get into it. Yeah. That formula that products over reactants. Yeah, and I'm gonna put that's on my next slide. I kind of prematurely told you all that, knowing I was gonna tell you that later. So the favored to mean just means that there's more products at equilibrium, and this one means there's more reactants at equilibrium. So far so good, guys? Yeah. That means the closed container is not open to the outside world. It's in a bubble. Oh, did that already? Check. Yeah.
Can we only calculate the equilibrium of closed containers, or can we do it of open containers?
I'll tell you how we can say what happens if it's open container. We won't calculate KEQs, but we'll say what happens to the KEQ. All right. So this information up here is the reason that we can actually get the KEQ. It's called the law of mass action. There were certain hypotheses that were supported, and then laws that were formed from those. Because what's happened is we realized that the concentrations at equilibrium are very consistent with this math right here. So we have a system, we have a BCE. You can write concentration of products over concentration of reactants, and you will have the equilibrium constant, which tells us information about the extent of the reaction. So, sorry. Whenever you write the concentration of the products, you always raise. I have something in my throat. I can't get this. Okay, so you can either put the concentration of the products over the concentration of the reactants. But whenever you do that, you have to look at the molecularity of the BCE. So this A and B are serving as exponents for the reactants, and that coefficient of C and D are serving as coefficients for the products. Exponents for the products. So essentially what we're kind of assuming here is that this BCE is the rate determining step, it's the slow step, it's the one that's determining the overall reaction. So I'm not going to say that a whole lot because we can only assume the coefficients are now exponents in equilibrium, always. In kinetics, you always have to choose the slow step to do that. So this is very rare for us to be able to say, oh yeah, easy, just plug it in. Okay. But with this, you'll see that I have two different Ks. This Kc means you're using concentrations. Kp means you're using partial pressures, right? So you're going to do the same thing. Partial pressure of C, raised to the C power. Partial pressure of D, raised to the D power. Partial pressure of A, raised to the A power. Partial pressure of B, raised to the B power. Same situation, except now I'm not using brackets because brackets means concentration, and I have to put partial pressure to the exponent indicated. And this is always at one temperature and one pressure. The K's change based on the temperature that you're implementing it at. And pressure, obviously if you change the pressure, you're going to be changing all these partial pressures most likely, which will change the K as well. One more thing about this, I think it's on the next slide, but I'll tell you what the value here in a second means, but whenever you have this K, if K is greater than 1, is the product number bigger or the reactant number bigger? Product number bigger. So what do you think, which side is favored? Products. If K is less than 1, which number is bigger? Reactant. So which side is favored? Reactants. You just figured that out without me really telling you anything. That's on the next couple slides there. And the K values that we are talking about are not the kinetics K values. So I'm saying it's independent of the kinetics constant. They do relate just a little bit, but they're irrelevant. They're not going to be used to calculate K's whatsoever.
Could you make a new numbers, like,
Epsilon or something. Well, I mean, in all your tests, you're gonna have K's. So AP exam. I don't know. Just be really prominent. K. Okay. And the actually, no, I put it here. The pure liquids and pure solids from a BCE are not in the equilibrium expression. The expression thing, the whole products of reactants, that's called the equilibrium expression. You never put solids or pure liquids there. Why not solids? Can you find the partial pressure of a solid? No, it doesn't have a pressure. Okay, can you find the molarity of a solid? What's the definition of molarity? Okay. Liters of solution, moles of solute. Does a pure solid have either one of those? No, it's not a solution. It is probably a solute, right? But you don't have anything to put it in. So we ignore molarities of pure solids because they don't have pressure or concentrations. They are constant in terms of their concentration, if they had one, throughout a reaction. And same thing for pure liquid. Pure liquid is just a solvent. So how would you find the molarity of a pure solvent? You don't. There's not a solution here, and there's no solute there, so you can't do that. So we ignore, when we put it into the expression, we don't put it in there for pure solids, pure liquids. I'm not going to prove you to the concentration of water. It's 5.55 or something like that. It's just a neat thing for me to do. I'm not going to do it right now. Sorry, you missed your fun. Yeah.
So I'm making K really big. Could you just say K equilibrium and then put
I don't understand your question.
like you know how K constant for X would be K and then say K equilibrium constant?
Oh yeah, you would. Yeah, and you will designate that as you go through. But we're going to get to more places where we designate. All right, so for this first one, let's do the first one together and you guys do the rest. Write the K equilibrium expression for this. I'll do K, let's do KC. Let's assume we have concentrations for all of these. That looks real bad. All right, somebody give it to me.
CO2
CO2 to the first. That's it, right? Why not? Why is that it? Solids and solids, ignore them. That's done. We're done. All right, next one. I'll just do this next one because I enjoy this. KC equals concentration of NH3 to the second over just H2 to the third to the first. Okay. Also for that one, I could have put partial pressure on all of this. Instead of putting the brackets, I could put PP. Pressure. All right, you guys do the last two. If I did that one, I could definitely do that. Sometimes I will give you concentrations on gases because in problems sometimes you'll see that. So you could do Kp is equal to partial pressure of NH3 squared over partial pressure of H2. You could definitely do it. Yeah, these are interchangeable for now. Yeah, I'll show you how we can convert between the two. All right, so you guys got the next two. Are you okay on those? And I think I'll put this on the top of here. Right before, left corner of your paper. I did, yeah, okay, good. I was making sure. That's all. Just the equations for yourself to look at in all your free time. I've had that from like third grade. My free time is when I'm driving. I'm going to school. That's about it. And I'm learning Italian. I'm going to school. Listen to a guy. All right. Do I have to do these? Can I just do one for fun? Can I do this one? Okay. Kc is equal to concentration of agua. This is water vapor, so you can calculate that over sodium bicarbonate to the second. Okie dokie. Artichokes. Alright, now remember Hess's law where if you took a reaction and you flipped it, what did you do to the delta H? You negative the sign. You change the sign. And this one, you're not quite doing that because there's no signs. All K's are positive numbers. Okay, so we're not going to be flipping signs because there's no such thing as endo or exo K's. So what we're going to do is we're going to invert the sign. Oh, dang it, that's not on the slide. That's on that slide. Okay, I'll say that again in just a second. I kind of already told you this. If you want to write some of this down, by all means do it. I'm going to give you the brief of it. So when the value of K is really, 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 really large, that means that you have a lot of products, lots, over small number of reactants. So that makes your number really, really large. That means you have a lot more products than you have reactants. It's called lies to the right. That's just the way to say it, right there. If it's a super, super large number, like 1,000, then there's so many more products than reactants. We assume there's no reactants left, so we have to say that's to completion. So like this number would be like between 1 and 100. If that number's between 1 and 100, you would just say equilibrium favors the products. If it's over 1,000, it's going to just go to completion. If the K number very small, that means you have a lot of reactants left over, and essentially a very small number of products produced. So it's not really happy about going in the forward direction. So you say it lies to the left, favors the products. Favors the production of the reactants. And what if it's like? So this can be like 1 times 10 to the negative third to 1 times 10 to the negative like 13th. I mean, it's a pretty wide range. It can get to be really small and could still say it favors the reactants. If it's like 1 times 10 to the negative 50, it so favors the reactants so much, the reaction doesn't happen. Right. Liam, you just completed my thought. Okay, so K equals 1, that means you have equal. This is the only time you would say the product's concentration equals the reactant concentration, because that's the only way that you're going to get K equals 1. It's the only time that they are equal. And that would be at equilibrium, and it exhibits no tendency to be favoring products or reactants because it's in a happy place. Sometimes. Reactants can get to be that way. And then, remember how rate constants were temperature dependent? K's are also, for equilibrium constants, are also temperature dependent, So like for an exothermic reaction, is heat produced over here or over here? Exothermic. On the product side, right? If it's endothermic, it's going to be the opposite. So in this case, this temperature, if I increase the temperature, I'm actually increasing the heat, which is a product. It's going to, in Le Chatelier's principle, which we'll do next week, it'll cause it to shift back and favor the reactants. So this is very, very, very temperature dependent. We'll actually do a lot with that. Remember Le Chatelier? Okay. Remember that?
Which one?
I still left and watched the
There's a lot of those.
Stay on the AP thing or something.
Yes. You can also say favors products, favors reactants. Okay, here's what I was going to say earlier. Whenever you have the Hess's law thing and you reverse the reaction, you put a minus in front of the delta H or you change the sign. This one, for a reaction, you have to do 1 over the K because there's no such thing as a negative K, so you can't put a negative K there. So you're just going to invert it, do the inverse of it. This is this multiplied thing where I spelled it really, really bad. That actually means add. Let me fix that before we start. Okay. So if a reaction, if you multiply all the coefficients by 2, so you're multiplying the BCE by 2, then you're going to square the KE, or the K equilibrium. That's because, like, when you did the whole A to the A power, when you multiply the BCEA by 2, then you're actually multiplying this by 2 as well. So you're actually squaring whatever your KEQ is. If you add up reactions, remember how you added it, like you canceled out the stuff on the left and right side that were the same? That's what I mean by adding up reactions. You actually multiply the K's. No adding K's, you multiply K's for every single BCE. We'll do an example like that down here. Yeah. So if you take a BCE and you reverse it, add over the K. Sorry, I should have said if you reverse reaction, then you do 1 over K. I just worded it weird. Yeah.
if the reactions are added, do you mean like two separate reactions?
Yeah, two BCs.
So we'll just multiply the two K together.
Yes. And then, you know how I like really stress units? I will not count off if you put units on K. I will count off if you put units on K there. Because there are no units for this K. Dun dun dun. Okay? So the reason why is because remember I told you earlier we summed up the two rate constants to make the big K, where I had like K forward over K reverse is equal to K EQ. What happens to the units here? They cancel each other out, so because both of these K's for the same reaction will have the same unit, they cancel each other out, so hence leaving us no K, no units for K. And also when you go between KC and KC, they technically have different units involved, so we just don't write units for anything. Okay? Okay. Here's this reaction. Our KC will equal what? Tell me the expression for that. Okay, N2O4 to 1/2. Okay, what's happened between this reaction and this reaction? Reverse it. So what you can say here, you actually have this on your paper, by the way. Yeah, that's K to the 1/2 because there's a 1/2 power right there. I mean 1/2 coefficient right there. So this is called K prime. This right here, this reaction, since it's reversed, it's 1 over the KC from up here. Big K, okay. So it's 1 over that, or what are you going to do to this? Just flip it. Which will just be N2O4 to the 1/2 over NO2 to the 1. So you can write it like, you can just, if you actually had a value for KC, you would just put 1 over that in your calculator and figure out what the new K is. Or you can invert the concentrations that they give you, just flip it. So that's a rule you need to remember. You'll have easy questions like that on your AP exam, like on the multiple choice, will say, what's the K value? Given this information, what's the K value? That's it. Like if it's double, if it's multiplied by 2 all the way, you square the K. If it's reversed, you invert the K. If you have to add stuff up, like I'm going to do here, you multiply the K's. So this is on your paper as well. I have two reactions given to you, and I put Hess law here, Hess's law, so that you understood kind of the concept, the canceling of the products and reactants. But I want you to solve for the KC for this reaction using these two reactions. So what can I add, or since we're adding these, what can I cancel out? That thing, okay. Anything else?
That's it.
No. Okay, so one of these left, two of these produced, one of these made. Good. Okay, so BC matches. What do I do to my K's? No, you multiply them. Multiply them, so when you multiply 6.5 times 10 to the negative 2 times 6.1 times 10 to the negative 5, you get K, I'm going to call this KC1, 2, you get KC3, which will be some number like I have here, 3.965 times 10 to the negative 6. You guys can do some things. I just want to give you it all there. Alright, that's KC. So it's just a matter of knowing your rules on how to multiply. Lexi, you okay? Okay. Yeah. Okay. Can I go forward? You guys are doing fantastic. You're going to get your homework done in class. Okay, so I've been using KC a lot. KP is a tiny bit different. So I call this the politically correct formula because that's how I remember the formula. This is the formula I'm talking about. I call it politically correct because it's P and then C, not C and then P. Okay, so the reason that we can't just assume our KC is equal to our KP is because of the ideal gas law. The ideal gas law tells us what the pressure is of an ideal gas, and we try to assume everything's ideal so we don't have to do that. What was that equation called where you have to adjust for real gases? Funky equation. It starts with a V. Van der Waals equation, right. Okay, so anyway, assuming everything acts ideally, we know we can't figure out the concentration of a gas, maybe just straight off the bat, but we can adjust this so it seems like we're calculating the concentration. Moles per liter is what concentration is. Molarity, what have I done here? I've solved for P, but I essentially have what's in? Moles per volume in ideal gas law is liters. So I've essentially set it up to kind of solve for concentration of a gas, but that RT is still there, so I need to multiply my concentration by the constant and the temperature at which it takes place. But instead of me doing all that, I can actually just take my Kc that's given to me in a problem where I solve for and use this equation. So instead of doing that for every single gas, you would do it just from the Kc in the problem given to you. So what happens here is that this N is moles of gas. So in the expression, you have to count the moles of gaseous product minus the moles of gaseous reactant, and that's to give you your delta N. Whenever you plug this in, though, you're going to put the number for Kc, parentheses, R times T. They have to be in the same parentheses and raised to that power. Okay, it's not T to the N, it's RT to the N. Okay? All right, question. Yeah. Because KP, yeah, I can cover that. K, we would like to say K is equal to K, it doesn't matter, but if you're dealing with concentrations versus pressures, the ratio of difference between the concentration and the pressure is the RT that from the ideal gas law. That's why we have to multiply by it right here. Okay, and R is the one with pressure, one second, it's the one with pressure, so it's got to be your 0.08211 because it's partial pressure you're trying to get to, and then the T has to be in Kelvin. Question? Yes, and that's you would divide by your RT to the N. Okay, can I go forward now? All right, the way you count on it since the first period, the way you count moles is you use the coefficients with your BCE. That's it. Do not look at the concentrations given to you. Count it with your BCE. I'll show you how to do that when we get there. Oh, speaking of, let's go and do that. Okay, this is on your sheet. I think you guys can just do this. You guys just start this. If you're watching the video, you can pause and do this. This is on your paper. I very well might show this for years to come, so. You guys can do 1 and 2 probably very easily. They're yelling. Poor Lexi. Alright, come and do one. I'm going to leave it like this for a minute. So, borrow this. On the exam, you would need to put partial pressure on all those so that they knew what you're talking about. All right, so the expression, thanks, you're good. The expression's good. That's the KP for this because they're all gases. You squared this one and you squared this one. Question?
Oh, no.
You do number 2? Okay, go for it. Reading and it says 1A. It actually just means 1. That's how you're going to approach this. Question?
What is the RT to the change in increment?
Number 3. Alright, so that was pretty easy. Nathan saw that it was flipped. So when you flip the reaction, you do 1 over the K. The K is given to you. The K for the reaction above is 0.25. So all he did was 1 over K is equal to 1 over 0.25. A dollar can take 4 quarters, so divided by 0.25 gives you 4. So that's the K prime will equal 4. Okay on this, June? Alright, the next one. At a particular temperature in a 1.25 liter flask, it contains 0.45 moles of hydrochloric acid, 0.29 moles of hydrogen, 0.45 moles of chlorine at equilibrium. So all these things we've been doing so far have been plugged in at equilibrium. We're going to do something else in just a second. Determine the Kc through this. So we have we have gases here, so we essentially might have our Kp given to us, which we can actually get right now. Actually, no, like, we're going to do Kp in a second. Let's do Kc first. That's the easier one. What is the reaction that's asking for when it says for the formation of HCl? H2 plus Cl2 gives you 2 HCl. Okay, so what's the expression? Oh, I'm doing Kc right now.
Okay, so HCl squared.
Yeah. And so this is the only one that's squared. The other ones are to the first power because of the coefficients in the BCE. When you plug in your information, though, you'll notice that you're given these things in pieces. You're given it as 0.545 moles and 1.25 liters. So you need to make molarity. You need to put moles per liter like it states here. 0.545 moles of HCl divided by 1.25 liters squared, and then over the H2 gas, which was 0.29 moles over 1.25 liters, and the the Cl2 gas is 0.45 moles over 1.25 liters. No, because there's, well, actually they will in this case because there's 2 down here and there's 2 up there, but you would get the methodology wrong because it's not plugged in correctly. So what did you guys get when you got that? 1.55 or 1.6, 1. Yeah, there's two 6 figs, so we'll go with that. No units, yay. Okay. So you should be okay with plugging in the pieces of information. You got to put it together though. Okay, and it won't always cancel out. So go ahead and put the liters down there. All right, for the next one though, we want to get Kp for the same reaction at the same temperature. Is temperature given to us? No. So let's see if we can work around that. We know the expression is K what? RT, thank you. Delta N. All right, so for this reaction, the way you would calculate delta N, actually, so we have Kc, right? We know R, we don't know T, so let's see if we're going to work around that. We can get delta N from up here. How many moles of gaseous product are there? 2, because there's a 2 coefficient. How many moles of gaseous reactant? 2. 1 plus 1 is 2. Okay, so delta N is 2 minus 2, which is 0. How does that help us over here?
RT is equal.
Right. RT to the 0 power reduces down to 1.
So Kc is equal to
Kp is equal to Kc. So the trick for these are, if you have the same number of moles, beginning and end, sorry, moles of gas. I'm always talking about gases here, okay? So moles of gas from reactants to products, the Kc will equal the Kp. What if you have more moles of product gas formed? What will the delta N number be? If I have more moles of gaseous product. So it would be a positive delta N, which would make which one larger, Kp or Kc? Kp larger, because when you take this times this to a positive number, that means this is a bigger number here. So then your Kp will be greater than Kc when you have a positive delta N. We have a negative one, it's the opposite. So you can kind of check your math like that too. Make sure you're in the right realm. Yeah.
What was the answer to that?
What?
What was the answer to that?
There are no answers today. Am I recording? Yeah. Yeah, okay, good. Oops. Alright, let's go forward. I got 2 more things to show you. Sorry today. I'm skipping that because I like that. Okay. There's just something also called R. It's called your reaction quotient. I mean, not R, Q. It's called your reaction quotient. And it's only for initial concentrations. The K that we've been working with was for what concentrations? Equilibrium concentration. So when you have your ice box, you have ICE. I is your initial. So in a problem, it might say, given these initial concentrations, which way does this reaction proceed? You have to tell me by comparing Q and K. So you find Q the same way. You do Q is equal to the concentration of products raised to whatever their power is over the concentration of the reactants raised to whatever their powers are. It's set up exactly the same for the K expression, but you're going to look at the value of it. If Q and K are equal, it is at equilibrium. Okay, it's at equilibrium because it's at the number it should be. It's equal to the K, which represents equilibrium concentrations. If you are looking at it and you say, K or Q is greater than K, What does it actually mean? That means this number, the product number, is bigger than what it should be. Because the only way you're going to get something greater than k is for the numerator to be too high. If you have too many products, what do you have to do to them? You can't take them out, it's a closed system. How do you transfer them to the reactants? You react them to make them form reactants, right? So if you have too many products, you force the products to react and to form more reactants. So that's proceeding to the left. So you're going to say proceed towards reactants. Proceed to the left or form more reactants. That's all this means. It's just telling me, do I minus from the product side or do I minus from the reactant side? That's all this is going to tell us. Because it helps us set up our ice boxes. If you have if your K value is larger than your Q value, that means you have a large number of reactants. Because the denominator is too large, the denominator of the Q value pulls down the value of it. So too many reactants, how do you get rid of them? Make them react to form more products. When you form more products, you're you're proceeding to the right, which is proceeding towards the product side. And I don't say shift here because I reserve the word shift for Le Chatelier's principle. So when we're dealing with Q's and K's, we always say proceeds. Proceeds to the right, proceeds to the left. Okay, we're almost done. Yeah. Yes, that K will be given to you. Good question. I meant to say that. Because you have to have something to compare to. I know your poor little hands. I'm sorry. I have ice boxes I want to do with you, and that's about it. Can I go forward? Maybe. See? Okay, I'm skipping dance floor. We'll do that tomorrow. Is this the last thing? Yeah. Okay. So this is on yours. We're over here on this side. I'm gonna do 1 and 2 with you, and I'll let you guys do 3, 4, 5. So tonight you're gonna finish the rest of that little problem set. There's 5 questions, and then you'll do these textbook problems, and I'll have it on the website. We have 15 minutes. We might well get this part all the way done. All right. Consider this reaction. Say we're considering it. In which direction will the reaction proceed? What do you need to compare? Q and K. K is given to us, as Heather said. Yeah? How do you get Q? Okay, so how am I going to set up Q with this reaction? And see how many of these are concentrations? So I'm just going to go ahead and put brackets here, okay? So bracket NO what? Squared. O2. And. Okay, so I have my Q. Q is equal, the setup is still the same. And actually, I'm going to leave it like that for Q, and I'm going to put initial. So really emphasize we're talking about the initial concentrations in Q. All right, so these are the initial concentrations given to us. So when I plug those numbers in, 0.1 molar squared, 0.1 molar, 0.1 molar squared. Do not use a calculator. What's the answer, Nathan? You're working too hard.
Oh wait, yeah, hold on. 0.1.
It's just 0.1. Notice that these two things will cancel. Okay. That's squared and that's squared, so they both cancel. So the answer is 0.1 molar. Okay, so that's Q. Compare that to K and tell me which way it will proceed. Okay, so Q is less than K. So that means that who do you have more of with the Q number here? Do you have more products or more reactants? You have more, no. You have more reactants. So this Q right here is still products over reactants, right? Okay, so if there's a really low Q, that means you have too many in the denominator, which pulls that number down. So too many reactants means you have to force it to form more products, which means proceed to the right. I just want to give you that underlying stuff because on AP exam they might ask you to say why. They ask why a lot. So justify your answer, that kind of stuff. So that's why. What do we just say? Proceed. Right. All right. Now, given these, you guys can do this one. You're given, and actually, before you start writing, I'll talk through it. you're given 1.323 moles of NO2, 0.168 moles of O2 in a 14.5 liter container. You can probably tell me which way it proceeds right now. Think about it. Why? Nope. Give me something else.
There's no NO.
There's no NO. If there's no NO, which is on the right side right now, I mean, it's a product right now, but it's not given to me. So if it's not given to me, I'm going to assume that there's nothing given to me initially of that particular compound.
That means the product will be 0 on the top.
So which way does it have to proceed?
Right.
To the right. Think about it like this, guys. You have no product. You have some of this product and some of that reactant, but you have no product there. You can't react this stuff if there's none of that. So it can't go that way. So it has to go this way. Logically that should make sense.
Mm-hmm.
Otherwise, proof K is equal to 0.168 moles of O2 over 14.5 liters times 0, which is the concentration of this that's not given to me, divided by the NO2 given to me, 1.323 moles, divided by my 14.5 liters. The only reason I'm doing this is because I'm using concentration, so I have to do moles per liter. Anyway, regardless, this is going to give me 0. 0 is less than K EQ. So if Q is less than K, it has to proceed to the right. Okay, but this is a lot of work. What I need to do is just say proceeds right due to the fact you have no product. Yeah. Okay, so that the mathematics won't work out, so you have to say it has to proceed to the left because you have to form those reactants. Okay, all right, you guys, if you can do part C if you wish. I'd like for you to do, oh no, I got number 2 with you. Oh gosh, okay, hold on, let me do this first. And this looks scary, super scary, like real big table and stuff. Let me make this less scary, there we go, okay. Less scary. And I want to make this I, initial, delta, which means change, and this is equilibrium. We have an ice table. Ice tables always have, it's like a little equals mark or whatever. So initial, how much is changing, to mean equilibrium. I have given to you the A plus 2B yields, or reversible reaction yields C, and I have given to you the initials for both A and B. What can we assume about the initial of C? 0. If I don't give it to you, assume it's 0 molar. Okay, what has happened to A? Okay, now the end, so equilibrium is 0.15, so what's happened to it? Okay, so we have minus 0.05 molar, 0.050 molar. But notice, I'm going to write this as A plus 2B yields C. Okay, notice there's one A, there's 2 B's, and there's 1 C. So this, what we're essentially going to say is minus X here, minus 2X here, and plus 1X here, because of the coefficients from the BC. Alright, so if this is 0.050 for X, what is this one for 2X? Okay, colors. Minus 0.100 molar. What's the final here? No, it's this minus here. 0.150 molar. And what's the final for, or sorry, what's the change for C? We're adding 0.05 here. So yeah, 0.05. Give me a thumbs up if you're cool with that. Alright, if you're good to go, you can do, so these are in chunks on this big table. You can do the next chunk and then I'll let you go ahead and proceed to 3, 4, and 5. Okay, so yeah, this is now my initial change equilibrium. So I'm starting now with this, the result of my first 20 seconds. I'm going to go down to my next 20 seconds. So this table looks real funky, I know. I tried a little bit too hard this one. A lot together. Minus. For now, yes. I could verify that by comparing my Q and K. but I don't have a K given to you, so assume yes. So you'll notice that this is the only thing given to us. So you're adding a specific amount here. How much are you adding over here? 0.025 molar. So you're minusing that much from here. And you're minusing twice that here because of the 2x nature of that. Okay. You have to look for the first thing, the only thing that's given to you, and in this case, the difference between here and here is you're adding 25 there, so it's 0.25, right? But this plus x, so since this is adding 1x because the 1c here, this over here, the reactants had to minus from the reactants in order to even to produce those products. So you're minusing the same amount from this one because of the 1-to-1 ratio, but you're minusing double it from this one because it's a 2-to-1 ratio. So I'm minusing double what x, because this is equal to x. This is equal to 2x, and this is equal to x. So I'm adding x here, I'm minusing double the x here, and I'm minusing 1x here. This will give us 0.125 molar, 0.100 molar. Alright, if you guys are okay on number 2, you should proceed to 3, 4, and 5. Ask me questions before you go if you need to on those. No, you don't. You only need to do 2 fragments like I stated earlier. Just like once you keep going, you can keep going. It's up to you.
I kept going on my chart, and I don't know, like, I think I might have done something wrong. Because I guess the internet stuff.
I mean, I can fill in the chart for you. When you get down to 80 seconds, you'll notice, Heather, when you get down to 80 seconds, it's 0.1, 0.05, and 0.1, right?
0.1, 0.05,
Mm-hmm. 0.1. At that point, you'll see down to 100 seconds that the C is not changing, right? So it's at equilibrium there.
So it should be like
0, 0, 0.
Cool. Wait, for B should it be negative?
Did you minus from?
Oh, you divide by times 2.
What did you for at 80?
Wait.
You guys proceed to 3, 4, and 5? Not anybody.
Yeah. What on earth are you doing?
Oh, it's because I gave you. Since I gave you. Can I see your hands? Do you have any right now? Right now?
No.
Oh.
I can wait.
Okay, then just move on to your top.
Yeah.
So you're in.
I got to a thing and it says I have to subtract negative. So I must have messed up something that would Hold on, I need to see what I did wrong. Well, that's where I did it wrong. And then Oh, you
I
can
was
skip me. I just wanted to see
Yeah, because it's at equilibrium, so since that concentration is not changing, nothing is changing. So overall, it's at that.
But
So this is right. Right. 6%. That's or that's but that's 0.05 here.
You're writing 0, 0, 0. Nothing's changing. Nothing is changing. It's still stuck there.
You say equilibrium started at
Equilibrium, it started at 80 and continued to rise.
okay, got it.
Oh, I just kept on videoing. Alright, so end of this video means you're doing 3. Everybody can do 3, I think. Yeah, you can do 3. 4, if you need my help on, I know I taught you how to do ice boxes, but if you want me to help you through that before you go, let me know. And 5 is easy. Cool. Out.